So picking up where we last left off, we're talking about this binomial distribution. And we see here we have our chart, x, p of x, and we're looking to figure out how we can utilize our calculator to generate this for us. So of course we could use n choose 0 or 4 choose 0, 1 6 to the 0th, 5 6 to the 4th. Or if we start looking at our distributions, where on our calculator we hit menu, and then we go to we're going to go to statistics now, and we're going to go down to 5 for distributions. And if you go all the way down to A, you'll see Binomial PDF. And if we're running 4 trials and the probability of success, which is 1/6, and then let's say we want 0, we get the exact same value here. And of course, we can go up to our number, hit enter, and then change 0 to 1. And then we can hit enter and change it to 2. And then we can hit enter and change it to 3. And then we could hit enter and change it to 4 and get the same values. Another option that we could do is create a list and spreadsheet. Now, I have beaten you all to the punch, and we're going to delete this formula. And you know what? Let's just do this for real. So if I hit Control Document, I'm going to hit Add List and Spreadsheet. We're going to say this is n, and then this is going to be our n probability. If you go to the equals line and type equals, we can start typing in our formula. And here's where I can go to Menu, Statistics, Distributions, and go to our Binomial PDF. This is 4. This would be 1/6. And optional, we're just going to leave it as optional. And so we're going to type comma n, and that's going to call, once we say that it's not a column name but a variable reference, all of the n values for 0, 1, 2, 3, and 4, all in our distribution for us. And that saves us a lot of time. So if we're looking back on the notes, we can see that when we use a calculator, we can create these distributions by using Binomial PDF. And of course, we can make a histogram, just like we've done in the past, and see that our numbers, 0, 1, 2, 3, and 4, is this descending or exponential decay type of function. So we can show the binomial of rolling 6 in 4 attempts, also using the tree diagram. Now notice how complicated this starts to look, and how much simpler if we just summarize all of these different options, because order doesn't matter, to get this probability of getting exactly 4 6s or 3 6s or exactly 2 6s or exactly 1 6 or exactly 0 6 in 4 tries. And once we see the benefit of utilizing our calculator and how fast we can do these types of problems, it makes our lives incredibly efficient. So take, for example, if a student randomly guesses at 5 multiple choice questions, let's say there's 5 options, find the probability that the student gets exactly 3 correct. Each question has 5 possible choices, and we are going to assume that all questions are independent of each other. So we have a finite number, check. There are only 2 outcomes. You either get it correct or incorrect. The probability of correct remains constant at 1/5 or at 0.2. So we're running through our checklist, and the measures are independent, at least we assume. So if we want to find the probability of getting exactly 3, we're going to do 5, choose 3, 1/5 to the 3rd power, and then 4/5 to the 2nd power. I'm going to just highlight that 0.8 and 0.2, those two always will add up to the total number, or n. So 5 choose 3 is 10 times 0.008 times 0.64. We get 0.0512 or 5.12%. We could just as equally likely do this by using our calculator. So if we go Binomial PDF, we go 5, 1/5, 3, we get the exact same value. In fact, let's do that. So on our graphing calculator, we're on a calculator portion. We hit menu, 6 for stats, 5 for distribution, and then you can hit the letter A. We have 5. The probability of success is 0.2, and we want 3. You hit OK. You get 0.0512. Now, just so you guys see, if I only have 5, 0.02, this gives me the entire distribution for my binomial PDF, and I would just have to go first, second, third, 0, 1, 2, and then 3 correct. Either way gets you the exact same answer. Okay, so the probability of getting guessing exactly 3 is 5%. Not that great. Now let's make the problem a little more interesting. What's the probability the student will get at least 3 correct? There's that fancy word again, at least 3. So this changes the problem. At least 3 correct means 3 correct, or 4 correct, or 5 correct. So we would have to take 3 plus 4 plus 5. Well, if you go back to those probability distributions and you saw that I gave you the last 3 on the calculator, let's just pull that up for a visual. If you look at 0.0512 and then 0.0064, then 0.00032, all we have to do is add up those 3 probabilities to figure out the probability of getting at least 3. Or if we have our probability distribution, we can see the probabilities and simply add them. We add them because they are independent events. So if a student guesses at 5 multiple choice questions, find the probability that the student gets at least 3 correct. There's a better way of adding. And so on your calculator, what we would need to do is utilize the second thing and go menu. So let's go down to a new line. Menu, statistics, distributions, and now underneath binomial PDF or probability density function is binomial CDF. And this is a cumulative density function. Interesting. So the number of trials we know is 5. There's 5 multiple choice questions. The probability of getting 1 correct is 0.2. We want at least 3. So the lower bound is 3. The upper bound is 5. We hit OK, and we get 0.05792 on the dot, which is exactly what we found. Now, we could also look at it as 1 minus, if we're going to do the complement. Well, what's the complement of at least 3? Well, that's from 0 to 2. And if we do 1 minus the binomial CDF, or cumulative density function, the CDF, the C part means cumulative. I think cumulative means add them up. We get the same thing. So to find the probability of at most X successes in N trials, we're going to be using binomial CDF. CDF finds the area, or all of them added up together. Remember, the calculator will only calculate the probability of X successes or fewer. To calculate the probability of X or more, you must find the complement and subtract from 1. To calculate a probability of 3 or more, you must find the probability of 2 or fewer and then subtract from 1. To calculate the probability of more than 3, you must find the probability of 3 or fewer and subtract from 1. Not many calculators offer that lower bound and upper bound. So if you're working with the TI-84, this is how you have to do the calculations. The binomial distribution is a distribution of values, all possible number of successes. Thus, as any distribution, the binomial distribution has a mean and a standard deviation. So what do we mean by that again? Mean is just the average or the expected value. And so what we can do is just take the number of trials times the probability of success and get the mean. That is our expected value. So this is pretty intuitive. If the probability of success is p and we have n trials, the likely number of successes would be n times p. If you roll a dice 6 times, you expect to get 1 6. Hence 1 out of 6. Now, the standard deviation is a little more complicated. So first we think variance, or sigma squared, would be n times p times q. So standard deviation, remember q is 1 minus p, or the veil, is the square root of n times p times q. Algebraic derivation is more trouble than provides benefit, but we can easily show that formula work. Like if you want to see it, I'll show you it, but just trust me on it. So to put it all together, a binomial probability model for Bernoulli trials, or binomial n comma p. We have the probability of a random variable has whatever number of success is n choose x, p to the x, q to the n minus x. Our expected value, or our mean, is n times p. And our standard deviation, how far we are away from the mean, is the square root of n times p times q. So I would put a star or highlight these 3 formulas, as many of them will show up on the AP formula sheet. So in the statistics class, students miss class 17% of class days. If the class has 12 students, find the probability of no absences on a given day, and then find the probability of 3 absences on a given day. Okay, only 2 possible results are here, absent or present, or not absent. Success is absent. Trials are independent, only 12 trials, and probability of success is 0.17, so we'll say p is equal to 0.17 for all trials. This qualifies as a binomial experiment. This is a Bernoulli trial, so we do the thing. N is 12, p is 0.17, q is 0.83. If we want to do 0 students are absent, well, the probability would be binomial PDF. We want a specific or exactly that amount, would be 12, 0.17, 0, and we get 10.69%. The probability of having 3 students absent is 12, 0.17, 3. So the probability of exactly 3 absent is 0.2021. Notice the probability of no one absent is 0.1069 or 10.69%. Always interpret your answer. Please, please, please get into that habit of interpreting your answer. Finally, we're going to talk about some geometric probability. So the geometric Bernoulli is simply to find the probability of obtaining first success after X trials. So this probability is intuitive and obvious if you look at what we had before. If the first success is on the Xth attempt, there have been X minus 1 failures before it. Thus, the probability is simply fail to the X minus 1 times P. So when we're looking at geometric probabilities, oftentimes there's questions about like the expected value. The geometric probability model for a Bernoulli trial, we use P for the probability of the success, Q is 1 minus P, or the probability of failing, and X is the number of trials. So we have our probability model, where our random variable is equal to X number of attempts until the first success would be Q to the X minus 1 times P, with our mean being 1 over the probability of success. And our standard deviation, if this follows, is the square root of Q divided by P squared. You'd be surprised at how many people forget this one. Or what is the, if I just go, what is the expected value? It's 1 over P, or the mean. Okay, so to find geometric probability, the first success is on the Xth trial. Okay, so if I pull up a calculator, if I want to get to the geometric probability, I go to Menu, and then Statistics, and then Distribution, and then right underneath my binomial BIFG. We want geometric PDF. So for our example of rolling a die and getting the first 6 on the 5th attempt, the probability of getting a 6 is 1/6. I want to know what is the probability that happens on the 5th attempt. So I just type in Geometric PDF 16,5, and we get the probability the first 6 is on the 5th attempt is roughly 8%. To find the geometric probability that the first success is on or before the Xth trial. So for example, art of rolling a die and getting the first 6 on or before the 5th attempt, we would use CDF, or the cumulative density function. So again, statistics, distribution, scroll all the way down. I went a little too far. It's H and I. So I, if we want up to, we want to add all of these together. We'll do 1/6. We'll go lower bound would be, let's say 0, 2, on or before 5. And if we type our lower bound to our upper bound, we should really say the first attempt, but 0, 1, about the same. We get 59.81%. So that's the probability the first 6 is on or before the 5th attempt. And that's actually summing up each one of those probabilities before. Whenever you think on or before or summation, we are thinking a cumulative density function. Okay. One more example before we end this. Let us stipulate that your good friend, Bart Simpson, never heard of him, is a 60% student. I don't know what that means. I don't know what a 60% student is, but let's roll with it. That is, he averages 60% on tests. Okay. His teacher gives a 50-question multiple choice test with 4 choices for each question. What is the probability that Bart passes the test? 60% correct? Okay. So I want to know, what's the probability that he gets 60 or higher? So I could find out the probability of getting 30 or more by finding the probability of getting 30 plus the probability of getting 31 plus the probability of getting 32 plus the probability of getting all 50 correct. Well, that's way too much work. What we would rather think of, instead of adding all up, what I'd rather do is say, what's 1 minus the binomial CDF of anything 1 below 30? So if I take the summation from 1 through 29, and then do 1 minus that probability, obviously that's 30 and higher. So we go on our calculator. We go to menu. We'll go 1 minus menu, statistics, or 6. We'll go 5, and then we'll go down, go to distributions, and then not binomial PDF, by binomial CDF. The number of trials is 50. There's 50 questions on the test. He is a 60%. Our lower bound is 0. Our upper bound is 29. Hit enter. We get 1 minus 50, or 1 minus that probability is 56.10, or the probability that Bart passes the test is about a 56% chance. That's pretty interesting. Second question, what's the probability the first problem Bart gets correct is the 4th question? So he goes wrong, 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 right. Well, there's only one way to do that. You get wrong, 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 right. Well, this is asking for a geometric PDF, because it's just saying up to, like, what's the probability this happens on the 4th shot. So I go all the way down to geometric PDF. 0.6, we want this to be on the 4th question, and it's about a 3.84% chance. Bart answers correctly is on the 4th problem. Okay, what's the probability that the first question Bart's What is the probability that the first question Bart gets correct is in the first 4? Notice that that wording is different. So instead of the fourth one, what is the probability that the first question Bart gets correct is in the first 4? So that means the probability that it's the first one, or it's the second one, or it's the third one, or it's the fourth one. So if we are adding, because that's what or means, we are talking about the geometric CDF. So instead of geometric PDF, we'll change it to CDF. And this one, 0.6 to 4, we hit enter, we get our percentage. This will sum up from the lowest to 4. Oh, interesting. Okay, well, what is the probability that the first question Bart gets correct is after the second? Probability that the first correct after the second? Well, I would rather say, let's do 1 minus the geometric CDF of him getting that up to the first or the second. 1 minus would be what we want. So if I hit enter, I get 0.16 or 16% chance. The probability the first question Bart answers correctly is after the second question is about 16%. So let's put a pause here. We've talked about binomial Bernoulli trials, and we've talked about geometric Bernoulli trials. The last bit is tying together what we talked about in Chapter 6 with the Galton board that we saw at the first part of Chapter 17 and the normal distribution. Where is this all heading? Is that we can create a normal model from all of this work. So I'll see you in part 3. We'll wrap up Chapter 17. I'll see you in the next one, Falcons.